let's go. Okay, great. Well, I just wanted to start streaming. Let me talk a little bit about what I want to do. I'm going to be streaming development on an emulator for the Casio Loopy. For those who don't know, the Casio Loopy is a system from 1995 that was primarily marketed at girls. It only came out in Japan. I'm going to show a little bit about it from the Wikipedia page here. So it's a 32-bit machine. I only had 11 games, so it's pretty limited in terms of the amount of content, but it kind of is interesting because there really aren't very many emulators for it. There's like a little bit of work that's been done in MAME, but it seems to have stalled, and I was in NodeConf Europe recently, and I was talking to Rachel Weil, and she said that she told me about this system, and she said it would be really cool if someone actually worked on this. Mostly people don't because it's, you know, primarily for girls, and I thought, you know, this would be kind of a fun little project. There's a lot of things that'll be kind of complicated about it. There's not a lot of information about the system. We know that it's a RISC SH1, although interestingly enough, MAME actually says that it's an SH2. So we'll start with SH1, and then we'll look at some of the opcodes and see what those look like. And if we see any SH2 opcodes, then maybe we'll implement those. But because there's not a lot of information, a lot of this is going to be debugging. It's going to be like figuring out what's going on in the system and trying to determine what exactly is happening. We have some information about what it's supposed to look like and what it's supposed to sound like because people have videos of it. But other than that, it's going to be a lot of just sort of like digging down deep into the data and seeing what it looks like and seeing how it works. So I've made an emulator before, a Game Boy emulator, which is kind of like the intro to emulators that a lot of people do. But I was thinking, you know, might as well try something a little bit harder. A RISC CPU has a lot of tricky stuff that will make it a little bit harder to you know, just hack up. So for now, what I'm going to do is take to show a little bit about what I have so far. So I have some docs. This is the documentation about the SH1 and the SH2. So what we're going to do, I've already looked through this a little bit, but I'm going to have to look through it some more and figure out exactly what instructions need to be implemented. The first thing I want to do is make a disassembler. So actually, I can show a little bit here. We have this ROM here. This is one of the games. And if we just look at the data here, we can see that there's a bunch of data at the top of the file here. This is probably like a vector of information. Like these are addresses, I think. And then this looks like it's actually starting to be code. So I already kind of messed around with this a little bit before. There's some online disassemblers that allow you to take code if you know what the CPU is, and then it'll disassemble it for you. So what I'm going to do here, just as a first thing, is first of all, I'm going to get this out of here. I'm going to take some of this code, and I'm just going to because I'm pretty sure this is code, and I'm going to open it up in Vim here. And I'm gonna paste it, and then yeah, I'm gonna take this part out here, and then take this part out here. Whoops. And I'm gonna put this into the online emulator. So let's take a look at that. I think this will take me to it. Yep, online disassembler. We'll start disassembling. And we can put in our platform. So we know that this is an SH1 or an SH2. We'll call it an SH2 for now. So there's SH2. And then we can paste the code in right here. Oops, that's the wrong thing. So let's grab this. Okay, so we've got some code here, and what we can see is that this already looks wrong. actually, no, maybe this is right. C701, so we're moving a value into R0, then we move a value from R0 to R15, then we do a branch to 10, which is down here, okay, and then we do a move of 18 into R4, and then we move 0 to R0, then we do another branch. So yeah, this actually does look right to me. Okay, that's very cool. So, yeah, what else do we have here? So what you can see actually is that the way this architecture works is that all the instructions are 2 bytes, right? So you can't actually store a 4-byte value, and so what I believe is happening here is that actually the address is being stored in the instruction stream, and that's why it's jumping over stuff. So you can see right here there's a 0908, and that should be the address that we load here. Well, so this one actually, this address doesn't seem to be coming through, but this one does. So you can see 118, there's a 09118C, so that's 118C. So it's basically showing you that it's moving a value from this address into R4. So what I'm going to do is try and basically produce a similar output to this, like so that I can basically read the file and just try and disassemble everything. And if I ever get stuff that doesn't look like data like this, then I can do the same thing and just do .word. So basically what I want to do is try and get the exact same output as this. So we'll leave that up here right now. And then the first thing that I want to do is basically, let's see if I can, yeah, I want to start with basically a makefile. So I'm going to actually copy a makefile from my Game Boy emulator, and we'll just pare it down for the stuff that we don't want. So having debug and release is nice. There's debug release. We don't need any of the scripting stuff for now, so we'll just leave it like this. And if we do this, it won't work because it wants to run cmake. So I'll just copy the cmake file from there too, and we'll pare that down as well. So 2017, we'll leave the WebAssembly stuff out for now. We'll leave in all these for now. We'll pull out all the Emscripten stuff because we don't want to bother with that just yet. We can add it in later if we want it. SDL2, I'm going to get rid of that, and OpenGL as well. I don't need any of that stuff. This is the basics right here, actually, and this is for debuggers and so on, but we'll keep it simple for now. So what do we have? We can get rid of the SDL parts, and this isn't bin.gb anymore. I was going to call this Loopika, so let's call it Loopika. Okay, and there's our files, and that looks pretty good. So actually what I usually like to do is have 2 windows. So we'll have a window here for Vim, and we'll have, and there's our cmake, and then we'll have a window here for building. So we can do build, and it's going to do some stuff, the cmake stuff, and then it's going to say it can't find the file. So that's perfect. So we'll add our file here, and let's just do the stupidest thing we can. Let's add this. Okay, and it says what? No rules to make the build directory. Why does it want to do that? So there's our out. Let's arm with that and see if we can get this to work now. Oh, it's in source. Okay. Yeah, let's do the same thing. So we'll kill this file. We'll make dir source. We'll move this into source. We'll go back to this, and we'll do our make. It still doesn't like this out build. I'm not sure what I'm not doing properly here. Probably seems like it should be making the directories. All debug. Alright, so I probably did something wrong when I copied from the CMake list here. So let's just see what that might have been. Let's just make sure I grab the right one. Yeah. So that looks good. Oh, I don't have a module path here, so that's maybe part of it. Yeah, I need a bin directory. Should be fine. There we go. Cool. All right. We'll close this. We'll go back to this. So there's our file, and then if we look in bin, there's our output file. Great. It does nothing. Exactly what we wanted. So first thing we can do is just do super basics and just have it open a file. So we know the name of the file, and we want to read it. And then we want to read from the file. So I'm just going to read into a buffer. We know it's 2 megs. But we won't do it that way. So we'll do read file, and let's have it return this information. So usually what I like to do is just have our result here, and we'll just do result error, and then we can have it return that result. So we'll do like file read file. And then we can have it pass in a buffer. So let's just make a buffer. Why not? Let's call it size. And then we need stdlib for size, and we'll pass in the buffer we want to store to. And for now, we'll just have it return error. Let's make this, yeah, no, I like it better like this. Okay, so then what we want actually is like this, and then do read file, read if read file equals error, we'll return 1, and we'll just print something error. Okay, and usually the way we do this, very simple, like I was doing before. We open the file name for reading, and then if this fails, then we error out here. Otherwise, we can get the length of the file by doing ftell, so we'll do an fseek on the file to, I believe it's like that. It's at the end, yeah. Okay, and then we'll do an ftell, and that will give us the length. So I'm pretty sure that's what ftell is a long, yeah. So we have to pass in the file, and we'll seek back to the beginning. And just to make sure that this is all working right, we can print out the length that we got. Just make sure that looks good. So we can build that. This is OK undeclared. That's because I did O capital K. There we go. And then we can do, and this will actually already load the file. So yeah, we're getting 2 megs. That looks good. So now we can read the file into a buffer. So we know the length of the file. So we can actually just allocate our buffer here. So we'll just do, actually we can allocate it directly into here. So we'll do malloc, and we'll cast it to the, actually you don't need to cast it in C. So we'll just do allocate length, and then we'll set the size to length. So let's actually call this size for consistency. And then what we want to do is fread, and I'm actually not going to check return from malloc because it's like one of these things that people do, but if you run out of memory, there's so many other problems that are happening in your code already, so just don't bother. So the stupid thing about fread is that it wants 2 values here that it's going to multiply because it's expecting to be able to read like fixed size records. We don't care about that, so we're just going to pass in 1 there, and then it's going to return to us. Let's just see what the return type is again. Is it size t or s size t? It's size t. So it's going to return to me how many it was actually read, so we'll just call it read. And again, this is really unlikely that this is going to fail, but we might as well just handle it anyway. Yeah, and I think it's this value, so we'll just make sure that that's right. So make doesn't like our comparison here because size is long. So what we actually want to do is just change this to size t because it's not going to be negative. I think ftell can return an invalid value if file wasn't valid, but again, these are things that like I don't know how much we actually want to care about. So we actually got an error here. That's probably because this is supposed to be 1. So let's see what that is. Yeah. So it's telling you how many records of size you can return. Again, I think it doesn't matter. If we want, we can do it like this, and then yeah, that's fine. Okay, but so then that's read it into our buffer, so we can actually check to see that we got real values here. So I'm just going to do a printf, and we'll look at the first few values. We'll print them out like this. Actually, let's just, and actually I'm writing in C, so you can't do this. I know most people are like, why are you writing in C? But it's fun. So we'll just print out the first couple values. And so what this will be is buffer data I, and we'll just do it like this. All right, and so this is not a pointer, so we'll just fix that. There we go. So here's a bunch of our values, 1400, 128, 1430. So let's, instead of printing a new line here, let's print with space, and then if I mod, let's see, if I mod 16 equals 0, then we'll print, whoops, a new line. Yeah, and it's not properly, you know, because it's 0 a mod, so we'll print a new line there, but whatever. I guess we can do 5+1. Anyway, so I don't like that this is spaced out weird, so we'll do that. That looks a little bit better. Still, it's a little strange. Why does it have a different length here? Oh, because it's, yeah, so we're trying to print out a character, but if the character can't be printed, So we can actually use isPrint for that. This is kind of pointless, but you know, might as well just do the basics, see what we can get. So let's just say isPrint, and actually let's get the data out. So we'll do our int t here, we'll get the data, we'll call it c, get our data out. That way we can do cc, and we can say if isPrint c, then c, otherwise we'll just print nothing. Oops. Okay, yeah, so we're seeing it spaced out properly. And if we look at the output here, we should see the same stuff. So what I'm seeing is OE, there's an OE, there's a 0, 0, 80, and so on, right? So we're getting the right data. That is very cool. So let's get rid of that. So now we're basically reading the data. We're ready to go. So now we need to actually try and figure out what we're parsing here. So when we go back to our online disassembler here, you can see that we don't actually want to start at 0 like we're starting here, right? Because this, I'm pretty sure this isn't code. We could see actually. Yeah, let's take a look and see if this looks like code. So I'm just gonna copy this. Whoops. We'll put it into a new buffer. We'll get rid of this trailing business here, and this part here, and we'll put it into our online disassembler. Yeah, so you can see this doesn't look like code. It's already saying it doesn't know what these values are. So we're going to skip that for now. So instead, what we're going to do is we're going to jump ahead to the location where we actually saw stuff that looked like code. So we know the stuff that looks like code starts at about 480 hex. So oops. Just to see what that's like, oops. We can actually read some values there. So let's just read a value at U80 hex. So we can do data. So we can't actually do it this way. So what we can do instead is just copy directly into val from our buffer. And we'll copy the size of uint32. It doesn't like that. I didn't define min-pop, so we just need to copy it in there. Okay, but we're not actually printing it out or anything. So we'll just print out our value. Yeah, so that's our 66F017C7. So if we go back to our XXD, we should see the same values here. Whoops, that's the end of the file. C7. So you can see that's actually the tricky part here is we're actually reading the value backwards. So if you look at what I printed out in comparison, there's C701, and there's actually a missing 0. So we can add, we can do this. Yeah. So what you can actually see is happening here is that we're reading in little endian, but it's actually meant to be read in big endian, and you can actually see that from the output here because it's actually specifying words as having the first byte as being the high byte. So we actually need to read our values and swap them or just swap them ahead of time. So what I'm going to do is actually just read, just have special routines for reading bytes of larger sizes. So we can do that pretty simply. And you'll see that like I'm going to do this all in one file. I just find that to be simpler. until we need to actually separate things out. Like I say, don't bother with more complicated stuff than that. So I'm not going to call this address yet. I'm just going to call this a value like this. So we know if we have a buffer, we can actually just read that value directly from the buffer. But, and this should be a U8. But if we have a 16-bit value, let's call this address. We actually have to do a byte swap on it. And I'm not going to do a byte swap. Actually, I'm just going to shift it and OR it manually. It's easier that way. Like so. And I think this will actually work even though these are 8-bit values, because they'll be automatically coerced to int. But we can check that. And then finally for this one, we'll just copy the value twice. This will be like this. This will be 16. And there's another 4 here. And 8. And so then this is 1. And this is 2. And this is 3. So now we should be able to read our value here. And we'll pass in our 480. It doesn't like something. So I actually have it built in so that I can hook this directly in. Yeah, so it doesn't like that. Again, then I'm passing a pointer and I'm using a dot. It's fine. Okay, and then I didn't call this address. And then there's our buffer, but we have to pass in as a pointer. Okay, cool. So now if we run, now we get the proper order. So you can see C7O16OF16, 16F06, which is perfect. Exactly what we wanted. But as I said before, the instructions are actually 16 bits. So we'll do this instead. I'll change this to 4. Okay, so there's our first instruction. Cool. We got instructions. Instruction reading. So now let's just read a certain number of instructions and disassemble them. Since we all know that we know they're all the same size, we can do it very simply. So we'll make a function that's called disassemble. And we'll pass in a buffer. And then we'll pass in a number of instructions. So we'll just do that as a size t. And then we'll have it printed out just directly. So for now, we don't, we're not going to do anything too fancy, but, oh, and then of course we have to pass in where we want to start from. So we'll call that address. And again, this is not actually an address because this is into the buffer rather than being into the actual layout of memory, but step by step. So it's kind of like an address. It's more like an index, but that's fine. So we'll take our disassemble function. We'll pass in our buffer. We'll pass in a number of instructions, and then we'll pass in our address. For now, we'll just put that in here. So this should be address. This is our buffer, but now it's a pointer. And then we'll just write out our address like this. So this is going to be we'll call it our PC. It's not actually a PC, but it's like a PC when you're disassembling. Okay, so there's our address right there. Pretty cool. So now, the next thing we want to do is actually figure out what this instruction means. So to do that, we're going to have to look at the list of instructions, which I have here. So the list of instructions, you can see by looking at this document, have a certain structure. So here's the instruction code, and this is for all the instructions in the system. So I think we can look at the tables basically starting here, and this will tell us everything. This will tell us all the different instructions that we want. So what I'm going to do is actually write out the instruction as a in binary, make it easier to see which instructions we're actually reading here. So that's not too hard. We can actually just write a function to do that. So I'm going to have write binary, and I'm going to call it write binary U16 and pass in the U16 value that I want to write. And so we're writing from most significant bit to least significant bit. So you can basically just loop through like this. And we never want it to, we always want it to print a fixed size. So we can just do this, right. And actually, yeah, let's actually put it in a buffer since we know it's fixed size. We can just do that. And actually, we don't even really need to initialize it to 0. So we know that it's going to be 16 bits, and we know that it's going to have a trailing null. So we'll just do that. And we'll put that as the null pointer. And then we can actually just go through and say, we don't even have to do it in the opposite order, which is always a bit confusing. You can just do it in this order and store the value. So we want to basically say if x and the current mask, which would be 1 shift left I, if that equals, if that's non-zero, then we write 1, otherwise we write 0. So that's pretty straightforward. And then finally, we'll just have it print out to stood out. So let's see, actually, yeah. So we'll just print out buffer, and actually, usually you're not supposed to pass in a non-const string for the format, so I won't do that here. And then finally, print out our value here. So this is in our PC, this is our inster. Our PC is actually address, so we'll do this here. Right. So we want inster. Okay. We'll put a space there. Okay. So let's see if this makes sense. So yeah, I did it backwards. Oh, and just so you can see how I did this backwards, C is supposed to be 1100. That's what it is there. And there's our 1. There's our 1 there. So yeah, it needs to be flipped around. So that's fine. We can actually just do that, I believe. Nope. There we go. So there's our C. There's our 7. There's our 0. There's our 1. Cool. Okay, let's write a couple more. So we actually have a num instructions. We can have it write, say, 10 instructions. So we'll scroll back down here and say we have an I, which is our index. We'll say for I equals 0, I is less than num insters plus I. Then we read from address, which now is inster plus I times 2, because that's the number, the size of each instruction. And in fact, it's probably simpler to just increment address by 2 each time. That way we don't have to update this either. So we'll do that, and let's see what we get there. It doesn't like comparison, so that's because we are using a size t and an int here, so let's change that. Okay, so there's our C7, there's our CF06, AA04, 4027, so on. And just to make sure we can do our XXD of our binary, we'll grep for OX480, we'll just grep for X80, and then get 3 lines around it. Oops, that's too many. So you can see here's our 480, C701, C6F06, 8427, 0908, 000, and so on, right? Okay, so that looks pretty good. And then we can also see that we're getting our binary values here, which looks really good too. So there's our E, there's a D, and so on. So these values all look pretty good. So now we actually want to know what these patterns mean. So to do that, we're going to have to go back to this document here. And what I'd like to do is be able to just copy these all out. So I don't actually know if this is going to do anything that I actually want, but we'll see. Nope. Why didn't that copy? Okay. But it copied without keeping any type of formatting, which is really annoying. So, all right. What can I do to make this a little bit less gross? I think what I'm going to do is try and see if I can find like an instruction list. So this actually looks pretty good. Oh yeah, this looks really good. So there's a bunch of codes here. Can you sort by code? No. This gives you all the information about them. Again, if I'm going to copy this out, will it give me stuff that I like? Not particularly, no. Better than the other one. But it also, see, it's also still giving me this, like, this is running up into this. Alright, well, I guess what I'm going to try and do is actually just do it mostly by hand, which is pretty lame, to be honest, but shouldn't be too bad. So what we have here so far is that's one. Yeah, so it's even line wrapping for me, which is like super annoying. So here's our list of instructions. Yeah, okay. There's only a couple pages of this, so I'm just gonna do it. You know, this is what programming is really like. Doing things by hand that you maybe shouldn't be. And this one actually seemed to grab a second line for some reason. So I'll just copy these out here. There's our swamp, and so on. Okay. Just to make sure, move W to extract, move W. So where's our move L? That was this move L. So is the previous one the move B? That's our move W. Move W, move B. So that's 0100, 0100, 010. Yeah, okay, that looks fine. Then we'll grab these. Oops. Really? Did it not copy this part here? That's super weird. This is what copying from PDFs is like. Real bad. And see, it's even adding in spaces. Yeah, I'm gonna have to figure out a better way to do this. In the future. future. I'll think about it a little bit when I see, and this is actually this instruction here. What is this one? Oh yeah, so this is the div u that didn't actually copy properly. It's because it has no arguments, I guess. So it should be calculation result. So this is div ou. Yeah, div ou. Okay. And then we'll copy some of them here. Like, what is going on with the selection here? It's like super wonky. Let's see. There's our. Why is that copying all this extra garbage? Yeah. All right. It's fine. We're just putting up with it. And this one is called DT. Where did the DT go? It like just did not get copied. Yeah, that's pretty weird. Okay, you know what? I actually might do this a different way, because this is like clearly not working well. So instead, what I'm going to actually do is take this buffer and actually move it back over here, and then we're going to minimize this, and then we're going to loop through, and we're just going to do this manually. Like, it'll be less painful this way. Because all we really want is to know the name and the value, right? We just want like this. We don't want any of the other stuff, right? And actually, you know what I might do is, rather than do it like this, I might actually, whoops. I might actually do it in a slightly nicer way, which is that we'll just look through and we'll find the values that we don't have yet, and then we'll add those in. It's nice to be able to decode anything, but like, this is turning out to be way too tedious for a programming stream. So instead, what we'll do is we'll just look at these top 4 bits. So it looks like these top 4 bits like basically give us a clue as to what we're looking at. So to get the top 4 bits, we can just shift down. So we'll do this. And then we can look at those and say, what do we have? And actually, what I'm going to do is just do and actually, it's probably nicer to have these as hex, because that's how we're going to want to look at them. So we'll just switch that over to this, and this is always 1, and then this is A, B, C, D, E, F. Okay, and so okay, have those values there, and yeah. Then what we want to do is, if we ever get one that we don't know how to parse yet, then we'll assert, and we can just fix it. So let's do that. So for now, what I'll do is I'll move OXC up because I know how to parse some of that. And the rest of these I'll leave them unused, and we'll move them up as we actually see instructions that use them. We'll move this down. Actually move that there. Yeah, this is fine. What we want to do is actually print out the instruction. So we know that this first instruction, because we saw it in ODA, the online disassembler. We know that this first instruction is let's grab that out again. Bigger. We're just going to grab out this chunk right here. And this goes away. Like so. So, and then we'll just save this as test. It's fine. Okay, and then what I want to do is just take some of this code and copy it back in here so we can look at it. Right. So we know this first one is actually a move A. So that gives us some clues about what to look for in our decoder. So we know that, let's see, where's our doc? Oh yeah, right. So we know that we should be looking for a move A. I don't see move A. So it might be that's an alternate mnemonic. Oh no, there's move A. So yeah, C, 7, and then a bunch of values. So that's very cool. So that means that we can actually just look, for this case, we can actually look at the rest of the bits and see if the value matches. So we'll just do if inster and this equals that, then we know it's a move A. And we know that the rest of the values, basically, the displacement is actually the low 16 bits. So we can just print that out as well. So we know this is a move A, and we know that it should be written as displacement PC R0. Is that right? Yeah, R0. Which interestingly, yeah, no, that's what it called it. They didn't call it displacement here, though, which is interesting. But I'd rather follow the instruction format from this document because I think that's going to be more accurate. So now we need to know the displacement. So we'll just get that out like this. We can write the value there, and I'm gonna create a new window, and I'll make this maximized. There we go. And then we can do our make again. Okay, so there's our move A, and it says it's displacement of 1. So that's actually wrong. So that's interesting. I think it's because if we look at our doc here, it actually says displacement times 4. So that makes sense, actually. You usually don't want to have a displacement of 1 byte because you're not reading unaligned values. So what we'll just do here instead is we'll just call this multiply by 4. Also, it looked like we were doing our right binary, but we didn't print space afterwards, so we'll just do that. Yep, so there's our move A4. Again, still not right, because this says move A8. So why is that wrong? So let's look at our doc again. It says displacement 4 plus PC. So we actually need to know what the PC is. That's kind of cool. Yeah. So in this case, we'll actually use the address to know what our oh, but see, yeah, so that's the difference here, is that we're saying displacement from PC, and this is basically just assuming, like, I know what the PC is, I know that it's 0. This is actually wrong. In this case, we don't know that the PC is 0. It's just sort of assuming for the online disassembler that it can use that value. So we'll leave it like this, because this is actually correct. It's displaced 4 from PC. In this case, PC is going to be wherever the current value is, where this instruction lives. So that's cool. So we have one instruction. Let's look at the next one. Next one is 6F06. 6F06. We can look on our online disassembler, and that's supposed to be in move L. So we'll look back and see if we can find a move L. Move L. So I know it's a move L plus, so it's probably this one, 6F06. Yeah. Okay, cool. So we'll pull 6 up to the top here, and then we'll say if the bottom is 6, then we know we have a 6. Yeah, we'll have a 6 and a 6, and then the middle ones are registers. So then we know that this is, since this is in the name, we can get rid of it there. So we know this is a move L. And we know that we actually have 2 registers, which are 4 bits. I'm just going to make those ints. That's fine. Yeah. So the top, the register name is N and M. So N is the top bits. So we'll take, we'll basically just take the instruction and shift it down by 8, and then mask it with that. And then for M, we'll take it and shift it by 4 and do the same mask. And then finally, we can just print out the instruction. So in this case, it's R, and then R, we'll do N, M, and we'll look at it. So this is R15, R0. That looks right, I think. So we did it backwards. Why is that? Yeah, so it should be M and then N, actually. And this one actually is supposed to be a plus. Like so. Okay, R0 plus, R15. And that looks good. Let's compare that. R0 plus, R15. Yep, cool. All right, moving on. Next one we have is A004, and it says that's supposed to be a branch. So we'll go back to here and we'll look for our branch. Yeah, okay, here we go. And it looks like branch is just anything starting with an A at the top, which is very easy. So we'll grab our branch, and we'll just say, Oh, we already know what it is. The rest of the values represent the displacement, and this is a delayed branch. So what we'll do is we'll mask off the low bits. You don't have to actually do anything there. This is the displacement. Wrap that up. And we don't need to do that. And this is a branch to a label. So we'll just do like this. And actually, I don't like putting these spaces afterwards, so I'm just going to get rid of the spaces there too. And then put, we don't need a space there either, so this is fine for now. Okay, like so. So let's take a look at that. It says branch to 4. That's actually wrong, again, because in this case, you can see it's actually branching to 10. It's because it's branching relative to the current PC. I think the way that I want to write that is like this. It's unfortunate because they don't really talk about it in the format here. It's fine. But I think it'll make it clearer when we're reading that like this is supposed to be a branch from the current PC. Okay, so moving on. We have a 4027. Okay, and we know that that's supposed to be LDC. So let's find LDC. LDC. All right, so it looks like a lot of these LDCs start with 4, and then they end with 7. So the one we're actually looking at is an LDC with an increment on R0 into VBR. So that's this one here. Yep. So we'll grab case for 4. Oops. And we'll pull out the value we want. So we know that this is true if the last 8 bits match exactly 27. Is that right? Yeah, 27. So we'll just put in a check for that here. If inster and ff equals 27, that looks good. Then we know that this is an LDCL. Again, we're writing it out below, so it's fine to not put in a comment. In this case, we know that it's at the 8-bit, so it's the same here, but we call it M. Right. So we'll put LDCL. This is R M plus, and then this is VBR. So let's look at our output. LDCL looks good. All right, so then moving on, 0908. So we know actually this one is funny because it's not a real instruction. We know it's not. The tricky part here is that we don't know that it's not a real instruction because our decoder isn't like complete enough. So what I actually want to do is have a default case here. Instead of having all of our cases here, I'm going to have a default case, which is anything we don't understand, we're just going to write out directly using the same format as described here. So, yeah. Actually, this can be 4. And I don't want a new line. Okay, so there's our 9.8, there's our 0, and this looks pretty good. Let's add a few more instructions here. All right, so we can see our next branch down here. That looks pretty good, but I believe we're actually not decoding this one right. So D401. right here. Okay, cool. So let's look at D401. We know it's supposed to be a move L. So let's find that one. All right, here's some move L's. We're looking for D, which will be 1101. There's a D. Yeah. So this one must be right because all the rest of the bits can be anything. So we'll do that. Like so. And we know that this is a move L. And then it's also displacement from PC, just like that other one. But then it can be in a specified register. So we don't actually have to do the if here. Because we know if it's got an OXD, that's what this instruction is. But we do want to know what register we're in. So this is register called N. We'll shift down by, by 8. Yeah. And we'll mask. And that's going to give us our N. Let's take a look. Okay, move L 4PC R4. Now let's just see if that matches R4. Cool. All right. This is looking pretty good. So now we need 2402. Yeah, we don't have that one. Okay, so 2402 is a move L R0 at R4. So move L R0 at R4. So it'll look like this. Yep, so there's our 2, and there's our second 2. So now we know if we start with a 2, we could have this case. So what we want to check is if the instruction's lower values are 2, I'm pretty sure that's all it is. Yeah. No, where did it go? It's this one. That one there. Then we know that we have an N and an M that we have to extract. So there's actually some structure to this. So we probably are going to want to actually pull this out at some point. But for now, I'm happy to just do this by hand because don't really know what we want yet. So this was the case up here. It's R M and R N. So that's M N. Let's take a look. Yeah, should be that one. Move L R0 R4. R0 R4. Cool. And then 118C is actually an instruction too. And that looks like a more complex instruction. That's cool. So it's a move L with, it looks like an offset before it does. My guess is that this is like basically read from memory. That's what this at means. So it's probably saying take R1, add 48, read from memory. And I guess this is the destination. Yeah, because it looks like, yeah, it looks like you can move 0 into R0. So this would be moving R8 into this location. So let's look for that one. So that would be probably like this, right? So let's just see if that's right. Is that a 1? Yeah, 118C. 118C. So this is cool. This is another one of these where it's like uniquely determined by the top 4 bits. So we can just do this, and we don't need to do any of that. produce a new Clang format file. So we just need NMD. And this gives us rm disp rn. So it'd be rm disp rn. We've been calling this disp, so let's call this disp here too. So this is giving us R8, 12, R1. R8, 12. And again, yeah, our displacement is probably multiplied. It does not say so. Oh yeah, it does right here. But actually it's this instruct, nope. Yeah, this one, times 4. So the other thing we're seeing here is that, like, yeah, our displacement is always, for an L instruction, is always going to be multiplied by 4. So that's something that we can do. Hi, Dazed Head. Stream is very interesting. Let's see how other thing works. Seems to be very much work. Yeah, it is a lot of work. And this is just the beginning. I'm basically just trying to get a disassembler. This isn't even implementing the instructions yet. This is just decoding the instructions so you can kind of see what actually the code is doing. So yeah, emulators definitely take a decent amount of work. I could have just grabbed a SH2, a Super H2 CPU implementation off the shelf. There's like a bunch of them. But part of the fun is sort of doing this yourself. So I don't know. The nice thing is that as we start to make progress here, we can sort of take, we can look at other emulators and see how they do it and say, oh, okay, is it, are we broken in some way, and use their code as examples. So, but for now, just using the online disassembler is plenty good. So yeah, so going back to our instruction here, we've got R8, 48, R1, R8, 48, R1. So that looks pretty good. Looks like we didn't write anything here. That's pretty weird. Oh yeah, so this is one of the instructions where we basically, we early out. Yeah, see, so interesting. Oh yeah, and so we're not even doing the default case. Question is how, not the first time. Yeah, I wrote a Game Boy emulator before. I'll send a link to that actually, if you're curious. This is the previous emulator I worked on. It's pretty fun. I got pretty far in it. There's lots more to do. Like, Game Boy is actually surprisingly complicated if you want to actually do it completely and get it very accurate. And I'm not trying to say that mine is very accurate, but it actually does pass a lot of tests. But yeah, it takes a lot of effort, and at some point it stops getting as fun because you're like, I don't know, you're just you're like trying to track down like bugs in very, very specific cases that are only in test cases that don't really affect games. Like, if you actually run most games, they work. So it's like very specific weird edge cases that you're trying to track down, and it's like, it's kind of interesting, but if the games worked, then like you kind of go, oh, who cares? I don't know. That's kind of where I'm coming to from that stuff. So in any case, so we've actually hit the end of this list here. We have 400B. That's this one here. So jump subroutine is my guess. I don't actually know this instruction, this machine code, this assembly language, so I'm going to be learning it along with all of you. So yeah, so JSR looks like the top 4 is, or the top 4 bits is 4, and the bottom 4 bits is always that looks like, what is that, D, 0D. Let's just see if that was where 0B. Yeah, 0, and that's A plus 1B, right? Okay, so we'll just do an else if here. And at some point, I'm imagining that a pattern will emerge here, and we'll be like, oh yeah, okay, I can see what the pattern is. But for now, I don't see it. So we'll just do it manually until then. So we actually have an M for this case too, which is very cool. So it's actually the same in both of these. We might be able to refactor that out, but for now I'm not going to bother. And it's 2M, so that should actually do it. Yep, JSR R0, JSR R0. Okay, then we have a NOP. And let's find that one. Oops, I really need to search. Where is our NOP? There it is. So yeah, it's just straight up 9. Cool. So we'll add that in. So this particular architecture is interesting. Actually, there's a number of architectures that do this, but you can see that they have this thing called a delayed branch. It's because the CPU is actually pipelined, and so what that means is that while you're fetching one instruction, it's executing an older instruction, and it's just kind of pipelined all the way through. The problem with the branch is that as soon as you do a branch, it has to basically throw away work. And so my understanding is that with these delayed branches, it actually continues to execute the later instruction, so it throws away less work. So you can basically tell it, like, this is an instruction that I want you to execute versus this is an instruction that I want you to just throw away. And that's what the delayed branch thing is. And so NOP is actually more useful than it is in other languages, or in other assembly languages, because I think for some instructions it always executes the delayed slot. So you can just put a NOP in there instead and it won't execute it. So we'll probably see NOPs all over the place. Yeah, there's a NOP, there's a NOP, there's a NOP. Oh yeah, but we're not actually decoding enough now. So let's change this to 32 now. Just see what we get. Yeah, so there's our NOP. Oh, and interesting, we're not getting those to come through. Why are those not coming through? Huh. Oh, it's because of the 0 here. Yeah, so what I'm going to do is, rather than have this be a default, let's see, what's the nicest way to do this? I want to basically just have a catch-all for the stuff that I didn't print anything, but I need to have it so that it even does it when this fails. So I don't want to have to mark everything that I print. Yeah. Okay, well, so what I want to do maybe then is have like a decode. Let's see, do I want to do that? And then I can return a value, whether or not I decoded anything. That's probably the simplest way, so let's do that. So we'll do a decode, and we'll pass in our instruction, like so. And we'll just grab the code that we have out here, and we'll put it into here. Whoops. I'm going to make this full screen, like so. Okay, and then rather than write this out, I'm going to actually return error in this case, which is a little bit weird, but just makes it a little bit easier. So we'll just do any case where we actually printed something, we'll return OK. every other case will break out and we won't print anything. Yeah. And then we'll do our decode. We'll say if decode inster equals error, then we'll print our this x inster, if I could type. Okay, so now you can see it's going. We can see our words again, which is good. Okay, cool. So what I'd actually like to do is, rather than having to come back to this all the time, I want to just copy this out. So I'm just gonna, oops, not that. That is too much to copy. Is it really not gonna let me copy this? Yeah, it's really not gonna let me copy this. That's really annoying. Come on. Okay, well, fine. I won't copy it. I want to see what we're basically at right now. So 900 should not be an instruction. It's not. We'll just look at all the ones that say word. So 402b, that is an instruction. That's jump. So let's implement that one. So that's 402b. So it should be in here. And we'll have to see what it's actually supposed to be. So we know it's a jump, so it's down here. Where were our jumps? Jump. So yeah, actually jump is really simple. It's just 4 at the top and then 2b at the bottom. Maybe with inspector. Oh yeah, that's not a bad idea. I want the inspector on the bottom. And why can't I grab the, oh, there it is. You can go to, oh yeah, see, it's got it's got them like in their own cells and everything. It's, yeah, I don't know. It's not going to be easy to copy out, unfortunately. That was a good idea though. Thank you. Okay, so what are we at? We were looking at jump, right? Oh yeah, jump. Yeah, 402b. So you know that if the bottom is 2b, then it's a jump. Yeah. Okay, so yeah, there's our jump. Cool. All right. So OE. That's nothing. Next one should be 604. Okay. So 604 is a move B. So we'll go back to that. I'll make this so that I can, it'd be nice if I could get this to scroll over. This is the problem with using Linux. Some of the software is not great, but it's all right. So yeah, we were looking for a move B, and this is a move B. Where was it? Here. with 2 registers that it can use for displacement. So that looks like it'll be this one here, I think. So 0, N, M, and then it's got a 4. So it should be 0, N, M, 4. Yep, that looks right. So we'll copy that one out. So it starts with a 0. And it ends with a 4. Yeah. So we say if it equals 4, that's a move B of Rm at R, always R0. Yeah, I guess so. Okay. To Rn. Yep. And that should be Mn. We'll return OK. Statement with no effect. If Mn undeclared, right? Because I need to pull those out. Is that the right slot for them in the middle? Nm. N is top, M is bottom. Yeah, so yeah, there's a lot of instructions that have the same layout, it looks like. Yeah, and there's our MB. So 4, 4, 6, is that right? 4 or 0, 0, 6. Yeah. Yeah, that looks good. Okay. Moving along to FE6. That is MoveL. And it's MoveL with this weird little minus thing. My guess is that probably, yeah, it's probably just a negative offset. We'll see. We'll see what that means. So yeah, MoveL with a minus. So that's this one here. Yeah. And let's just see if that looks right. That's a 2 in the top and 6 in the bottom. So 2, 6. Yep. All right. I'm starting to see sort of the general structure of instructions here. So we already know that's a 2 in the top, and we'll look at a 6 in the bottom. And we'll pull out the other 2 registers, right? Because there should be. It's easy to sort of lose track of what you're doing. Let's see. This one, MoveL. Yeah, so it's Mn. So it really is basically just that, right? Yeah, so there's our 14, 15. 14, 15. Yep. Okay, cool. Okay, moving along. RF22. RF22. STS. I have no idea what that is. Maybe store status. So it stores the status word. Yeah. STS. PRRN. Is that the one we're looking at? 4. So it's not this one. Oh, here we go. STS PR. Yeah, PRRN minus. Yeah, so it is this one. Okay. So that starts with a 4 and ends with exactly what we see here, which is 22. So yeah, 22, and then the register is in there. So we'll say if the bottom is 22, yeah, so definitely seeing a pattern here, right? There's FF, FF, and it's just checking bits here. So probably all the 4s have this exact same structure. That is my guess. And this is STS L PR R at R actually it's called N. Doesn't really matter, but I'd like to keep it consistent if we can. Yeah, so. All right, there's our STSL. Yeah. All right, I think we've run through all of them here. So now this is actually, I almost feel like I want to do something where I can catch potential error cases, like catch the word cases, and yeah. So I almost want to know that it's invalid. Like I've already handled this one, and then yeah, okay. I think I'm going to do it that way. So what I want to have happen is I want to have this assert. Of course, I need to include assert. Yeah, so this is blowing up already because it doesn't know what 0908 is, and we know that's an invalid instruction. So we should encode that into our decoder. So for now, what I'll say is there probably are other instructions, but for now I'm going to say that we know that this is a word. So I'm just going to return error early. This is kind of ghetto, but like rather than hitting the assert at the bottom here, it's just going to print out word here. So that's fine. Okay, so then we're going to get this new one here, which is E000. Again, we know, at least according to this, wait. Is that the D401? Oh yeah, this is up here. Yeah. Oh, that's an actual instruction. See? So this is good. It means I actually caught an instruction I should have implemented and I missed. So yeah, okay, E0. Yeah, the benefit here is that eventually I'm just going to be able to disassemble a bunch and maybe even disassemble the entire file, because like why not? And then just catch all the things that could possibly be instructions, you know? So we know this instruction is a move, looks like immediate into a register. So it's probably this one right here. E, yep, okay. So E is easy. We can just E for easy. We can get the N register out. I'm getting pretty close to wanting to have a function for this. And we can get the immediate out. Which it says is sign extended, so that's kind of cool. We'll probably want to incorporate that at some point, but for now, I don't think it's necessary. So, yeah, this is okay. We'll do it like this. So the displacement, we actually do want to do a cast here. So what I'll do is I'll cast this to an N16T, and then I'll cast it to an int, and that'll do the sign extension for us. And that's our N, and I think that should work. This one declared, right, because it's immediate. Yeah. Oh, right, but then I need to return OK. There we go. Okay. Oh, great. So we actually ran through the entire thing and didn't blow up. Very cool. Okay. So let's bump up our number. I mean, why not, right? All right. So a bunch more stuff, and then we blow up 7E01. 7E01. Yep, that's here. So that's an add. add immediate. So we'll find that one here. 7E01. So it looks like 7 is just a straight up add immediate. Makes sense because that's such a common instruction. They probably wanted it to be like it's easy to decode. I don't know if I had to guess, not knowing anything about hardware. So I'll just copy an example here. Actually, it's more like this one. So we'll do this. This is add immediate RN. But it's not sign extended. At least it doesn't say it is, so I'm going to assume it's not. Of course, I have to return OK. Yeah, okay, there's our add. Next one, 3E23. Ooh, compare. Okay, compare greater than or equal to. And we can see that here. Anything special about it? It's just compare two registers, looks like. Yep, compare two registers. So it starts with a 3, and it looks like a bunch of comparisons are starting with a 3. And we haven't actually seen 3 yet, so that's cool. So the one we're looking at here is GE, and it's the low 3. So we'll just say if the low ones are 3, otherwise it'll fall through. And we know we've got 2 registers, so we've got this. Oops. And yeah, so it's a comp GE RU RU. Paste this to your console, maybe this helps. For extracting the data. Let me see. Oh, I see. This will like extract all the stuff. Cool. All right, I'll give it a shot. Why not? Save some time. Oh yeah, look at that. Nice. Cool. Thanks a lot, Dazed Head. Yeah, so let's just copy this out. Yeah, this will save me from having to switch back and forth. Although I've actually kind of got a nice little nice little sub here, but that's fine. I'll let's see. I'll move this one over here, and yeah, see this events window is like really screwing everything up. I'll do that, and I'll just switch back and forth to it like this. That's fine. Okay. Cool. Yeah, this is a little bit easier. Although it didn't seem to copy everything. Did I just not see the entire? Huh. Oh, this window is like going crazy. What just happened? Oh, that's expanding. I see. Yeah, that's weird. Yeah, there's a lot of shitty HTML structures. I might have missed something. That's all right. Don't worry about it. Yeah, I totally appreciate it. It's actually really, I mean, it's nice to have at least some of it here. And actually, yeah, it's got a few more instructions that I think I have to implement, so I can just look at this instead of looking back over. So it's still helpful. So yeah, I definitely appreciate it. Yeah, there's our comp GE. And then if we return OK, that should be fine. So we've got R2, R14, and yeah, R2, R14. So yeah, totally. Thanks again, Dazed Head. Okay, so next, BF, which is what we're seeing here. I have no idea what that is. BF. BF. Oh, branch forward? Yeah, that must be it. Okay, so it looks like it starts with 8 bits at the top that are fixed, so we can use that to detect. So the 8 bits are 8B. So we already know 8, because we're using that as our initial test. It actually might be the case that that's not the best initial test, but like, we'll see, you know. So we'll say if inster and that equals B, then we know it's a BF, right? Because the rest of them are just the displacement. And the displacement is weird. It's like times 2 plus PC if t equals 1, no op. If t equals 0, if t equals 1, no op. Huh. Okay, but that's the implementation of it. So we don't really care about that. We just want to care. We care what it looks like. Again, this is just for the disassembler. And so the way it should be printing is, all right, we have it here, BF with a big old address. So I'm gonna print it like that. Is it gonna be 32-bit? Yeah. This is the displacement. So what I'm gonna do is say this is the displacement. Like that. And then look at this again. This times 2 plus PC. So I'm going to write it out like this just so that it's clear to me what exactly is going on, because otherwise these things will be like pretty unclear. So yeah, again, return OK. There's our BF. PC plus 2 times blah. Yeah, OF08. Let's just see if that was what this was giving us. It's giving us 54. That's actually a bit weird. Oh, I wonder if this is negative. Is this negative? It doesn't say that it is. I'm just wondering why, because it would make sense, right? Like if, because F8 is a negative number if it's an 8-bit value. Where did it go? Here. Yeah. So we're basically pulling out this part here. Yeah. Which would explain it would be a negative branch. I'm not going to worry about that for now, but that is worth noting that this is probably meant to be negative. Okay, moving on to the next one. Did we parse that properly? Yeah. So the next one is 6001. That's a move W. So let's find that. Move W. Move W. Move W. It's probably this one. Nope, not that one. It should be at R0, R0. So it should be this one. Yeah, there we go. 6 and a 1. So it's got a high 6 and a low 1. So we already have a high 6 here where we check for 6. So let's just do the same thing and check for 1, and then we'll pull that into here. This looks like it's basically the same except for the add is on the first, yeah, so it looks about right. So there's our move R0, R0. Again, we gotta return open. There's our move W. Okay, B0, F8. Okay, so now we're outside of the range here. But maybe if I scroll down, oh, that's why I haven't copied anymore. Okay, well, let's copy some more. So I'm going to fill that file, open up our test.txt. How do I want to do this? I guess I probably want to just copy the data out. So what I'm going to do is I'm going to do the whole thing. Just why not? Let's see how big that file is. So yeah, it's not even that big. Okay, then I'm going to do, oops. And so we went through a bunch of stuff here. Let's just do this part here now. And actually, we know what we got to the end of. We got to 4F6. Oh, but we're starting at 480, so wherever that actually puts us, it doesn't matter. I guess we can look for the actual instruction. So the instruction was B058. There it is. So we don't really need to include this stuff. We'll just copy, yeah, let's copy some lines here. Go back down. It won't even let me scroll down. What's going on here? Oh, it's because it shrunk the window. Alright. So there's our BF08. It's a BSR instruction. I think that means bit scan right. So let's take a look. Oh no, branch subroutine. That makes more sense. Okay, so branch subroutine. We saw that that's a high of D. Just to make sure. No, B. Yeah, B. Okay. So it's B, and then basically the rest of it is the displacement, the label, which is ×2 plus PC. Okay. So we'll go back to B. We actually don't have a B. So we actually know that this particular instruction is only used for BSR. So that's cool. Transfer and like that. Okay, and then now that's PC plus disp ×2 plus PC. So we did it like this before, but actually this is probably nicer. And we wrote it out like return our OK. And run it. Okay, there's our BSR. All right, we're churning through stuff now. Yeah. All right. Well, I would say let's do one more of these and then see how much more we decode, and then I'll see how I feel because I'm already getting a little raspy. Okay, 8800. Let's see if I can find that in here. Here it is. Comp equal. So it's comparing an immediate to a register. So we know that's 88. So we'll put that in here. So it's not this. Let's see if we can find that instruction. Looks like 88. Yeah, so it's just top 88. Yeah, so this actually has the same structure. It's actually looking at the same bits. So basically I want to know, is that one 8? And since this one is less, I'm going to put it up here just because. 3:33 a.m. Dang. Yeah, I'm in Oakland, California, so it's actually not that late. It's like 6:30 p.m. But I've been going for 2 hours now, so I should have had just some water or some tea right here. I have nothing, which is why I'm like, so yeah, this is comp equal, and it's immediate with R0. So this is actually immediate with R0. I think that's right. Yeah. Oh, and this is interesting. So basically, the way that comparison works is that it writes into this T register here. So T, rather than like a bunch of like 8-bit CPUs have like a flags register, but this looks like it just has one bit, and it's like sort of your responsibility to do the comparison ahead of time, which is honestly nicer in a lot of ways. So I can see why they did it. Okay, so there's our comp equal. Man, 3:33. I sometimes stay up that late, but I try not to. Let's see. So there's our comp equal. Oh, now we're in a BT. Oh wow, look at that. So this is giving us a giant, weird, yeah, giant value to jump backwards to. So we know BT. Yeah, so BT looks kind of like BF. The only difference is this one bit right there. So it's actually, what is that, 889? Is that right? 89. Yep. Okay. So 89. It's right next to the one we were just doing. And then the immediate is disk times 2 plus PC, so it's the same. Disk times 2. You know, it's dumb. I should have just done I should just multiply it in here the way I did all the other disks, because it's const. Like, why make people? Oh, not this one though. Wait, yes, this one, because this is actually supposed to be BT. Yeah. And actually, this can't really be. 16-bit anymore because it has to be multiplied by 2. Does that look right? Yeah. Do I have any other times 2s? I don't think so. Oh yeah, there's one. Yeah, so this is another case where I should just multiply it by 2. Like, I don't really care what's actually in the value. I want to know what the actual value is. And I don't know what PC is, so I can't actually test it, but I should do as much information as I can. So, where did that go? Oh yeah, okay. So there's our comp BT. Wait. Why do I have an R0 in there? And this should be like that. Comp BT plus blah. So it is a bit weird that the values are so different between this and the online disassembler. Because this is clearly doing sign extending. Yeah, I'm not sure what's up with that. Oh, you know what it might be? It might be that it's getting confused because it's like it wants to branch before the code here. Yeah, that's probably what it is, and so it's just it's wrapping around to a giant negative value. I still don't quite understand why that would be, but because like it doesn't say anything about it being sign extended or anything. I don't know. I'm gonna have to look at the actual. There's like, right now I'm just looking at sort of like the high level description of the instructions, but like if you scroll down, it'll start telling you about all of them. Like, so there's BF. Yeah, so 8-bit displacement is sign extended and then doubled. I see. So actually I am writing out the wrong values. So okay, I should probably fix that. So rather than double these, I need to first sign extend them. So this will be int at and then extended to int and then doubled. And same with BF or BT probably. Sign extended and doubled. Yeah. And then yeah, do I want to write that out as a? Yeah, it's probably okay. Okay, now I'm getting values that look like what they have with all these Fs, so that's cool. I wonder if I'm getting these values too, like this BSR B0, BC. It's probably because PC is C, yeah. So it's already added in the PC for me. I like having the PC separated out, so I think that's better. Okay, I'm pretty happy with this. Let's scroll down some more. What do we have here? Why is this? Oh yeah, so because anytime we do disps here, they're baking in the value, so that's not helpful. Finally we get to 45D0. That looks like here. Oops, I lost it. Yeah. Which we just need to basically say is not an instruction. So okay, so we have our 45D0, we're saying that's not an instruction, and then we have F1C0, what's that? Also not an instruction. Alright. We don't have any Fs yet, though. I have a feeling this is going to hide errors, but you know, catch them later. Let's see if we're missing anything here. 894. 894. We actually got that one. We're blowing up on 8E58. 8E58. That's also nothing. Is it 08? No, 8E. Ah. 99B0. 99B0. Okay, that's a real thing. And actually, did we get the add 64? We did. This is really the fun part of when you're working on an emulator. Like, this is just the disassembler, which is like, you know, step one. But it's like really cool when you're like, oh yeah, look, it actually works. Okay, so we want to move W with, what is this? This must be a displacement. I don't actually need to keep this around. Oh yeah, I'm looking here. Okay. So move W. So move W with the displacement. That's a 9. Is that what we're saying here? 9B. Oops. 9B. So basically all 9s are this move W with displacement. Wow, okay. So, let's grab one of these. And again, the move W displacement is the low 16 bits, and then the N register is the 4 bits above that. So I think we have an instruction that kind of looks like that. We have to do like this one. This is move W. What is it again? Disp PC. Oops. So this is actually displacement of the PC into Rn. We'll call this displacement. We'll call this N. And displacement is times 2. You know what I wonder? I wonder if these displacements are assigned values as well. I'll check on that later. Times 2. 352 PC Rn or R9, I mean. 99BO. Yeah. So there's the R9. 1EE. Huh. So we can actually check and see the calculation that they're doing, because they're adding in the PC directly. So you can actually just do OX1EE minus 8A. There's 356. So I was doing 352. Again, the trick here is that the reason that those values don't line up is because of the pipelining, because the PC isn't actually here. The real PC is actually down here. And that's the PC that ends up being used for all calculations. Which is why I didn't really want to include it, because it's like I think it makes things more confusing. It'll be clearer when you're disassembling with the data in the actual memory map, because then it'll actually have the proper offsets. But for now, it actually doesn't make any sense to include those. like the online disassembler is doing, I think. So we actually got to the end of this chunk. So we're decoding, yeah, we're decoding quite a bit. Trying to decide if I should do one more chunk and see how much I can decode, or if I should stop for the night. I'll do one more chunk. One more chunk. So we're actually at the end of this bit of data here. So I'll just double it because I have a good feeling about these. All right, so we actually were able to get through quite a bit. But then got stuck at 2231, which won't be in here, so I'll have to copy it out. Let's see, 2231, way down here. So that's pretty cool. We actually made it through a lot of instructions, just to make sure OOB should be the one before. So yeah, that's right. So I'm just gonna copy that, and then copy this. Actually, I'll copy more than that. Let's copy that much. And we'll put it in here. And scroll back up to the top. And what were we blowing up on again? 2231. So that's this one here. Move W R3 to @R2. So I'm going to hide this because we don't really need to look at it. And we don't really need this anymore. Alright, so we're looking at O2, and if I'm right about the layouts here, we should be actually looking at the bottom 4 bits, and that's going to tell us what we're actually looking at here. So that'll be interesting. But we know that it's in move W, so let's look for that. Move W. Move W 2. Move W. That's a move W at. So there's a 2 and a 1. Is that the one we want? I think it is. Yep, 2 and a 1. Right, so we're looking at the bottom bits, and it's a 1 instead. So this is pretty cool. This is definitely making the decoding simpler when it's like pretty regular like this. And actually, if you look at the document here, it actually talks about the instruction formats. So there are like, and it shows you the different structures, and so it's not surprising that they fit into these patterns. I wonder. Oh yeah. Okay. So this is what this is what I should have been doing. It actually spells it out right here. It says XXX is basically the instruction code. So you can actually look at the patterns here to determine what kind of code you have. But in general, the top ones always have some amount of code. So really what I should do is I should just have it decode the proper format, and then I can pass them through. Yeah. That actually would be kind of fun to just clean this up a little bit, because then it'll make it a lot easier to add new instructions as well. It'll be much easier to decode. So let's see. Oh, but how do I... The trouble is that not all of them match the appropriate pattern, so you kind of have to know what values to expect. Yeah, so it's actually easier to do it this way. The benefit will be, once I know the instruction format, I can basically look for certain patterns, and then I can just map them directly to this and then forward the values through. And that'll make the disassembly like really fast and easy. But again, I think it's still easier to like sort of do it by hand like this, just to sort of get a feel for the format. Anyway, we were looking at 2231, which was a move W, which we had determined was this one here. So this is a move W. I think, I actually think that's it. I think this is the exact instruction for it. And of course, oh, I did do a return. Okay. There's our 2231, and that looks fine. And we do it a couple times. Okay. So then there's our C106. And if we look at our disassembler here, yeah. Oh, we got this GBR thing. I actually don't know what GBR is. I think it's like a base register. So it's like used to basically add in offsets, like a common offset. So what we're looking for is a move W with a displacement in GBR. So like this one. That must be it, except for it's this one is a store, not a load. So wait. Yeah. Okay. So it's this. Cool. Okay. So looks like it's always R0, and the displacement is just stored in there. So we can do that. So it's a C1. And again, we're just looking at these 4 bits here. Yeah, so we know it's a C and then it's a 1. So rather than it being 7, like this case, we're looking for 1. And we're still pulling out a displacement. So this is a move W disp plus GBR into R0. No, the other way around. Like so. But it's a displacement by 2, not 4, because it's word sized. Okay, where did that go? Oh yeah, it's right here at the end. All right, so clearly we basically already parsed all the instructions for this first chunk. So yeah, this is pretty good. Pretty good indeed. And just to make sure that we're looking at the right values here, yeah, R0 12 GBR, R0 28 GBR, R0 12 GBR, R0 28 GBR. Yeah, that's pretty cool. Oh, yep, but see, this is what I was worried about. This one actually snuck through. This is a real instruction, and so did this one. So a bunch of these actually snuck through. It's pretty easy to miss now, which is annoying, but yeah. So, okay, I was lying a little bit. What we really need to do is grep for the words and make sure that none of these words are actually instructions. Just to make sure. I'm pretty sure about these first ones because we already looked at them, but like, yeah, so there's that FFF, that's here. Yeah. And then we have a 0. Oh, that's here, okay. And then 668, so that's fine. Then CO5. Yeah, and so that one's a real instruction. And then OOB and then 431E. Those are all real. Yeah. That's fine though. So, oops, I probably actually wanted that. So the first one is 668. Is that right? No, that one's actually not a instruction. So it's CO5. And actually, how best are we going to figure that out? I guess we can do this and find. So it's at 644. So it's here. So it's actually right after the 668. So it's this one here. Move W R0 with the displacement. OCO5. So that should be one of these. Where is it? Move W R0 with 2 registers worth of displacement. Oh, it's this one, right? OCO5. Yep, that's the one. Okay, cool. Right at the bottom. So it starts with a 0. And the bottom is 5. So it's actually very similar to this instruction here. In fact, that might be all I have to do, except for increment this to 5. Yeah, looks cool. Okay, so the next one is this OB, which should be 88 PC. Let's see. Oh, that's not how they're going to list it though. R3, R2. How are they going to display this? Well, it's probably this RTS. So OOOB. So RTS. There it is. Oh, and it's got a fixed name. So yeah, this is another one of those where we can just do this. Like that. There we go. And then 431E. So let's take a look. That's an LDC GBR. So I'm guessing LDC is like load constant, something like that. I don't see it. Where did it go? I already did one LDC. Yeah, here we go. LDC GBR. Oh, it's not load constant. It's like load control. It's probably like a control register. Yeah. So it's basically the same as LDC VBR. Did I already do that one? Well, I don't know. Anyway, the top is 4 and the bottom is looks like 1E. Let's see if that's right. 1E. Yep. So top is 4. Bottom is 1E. So I'll just put that right in the middle here. This is LDC GBR. Yeah, RM. Oh, but it's not at. It's just LDC GBR. LDC R3 GBR. LDC R3 GBR. Okay. That is cool. Awesome plus Manjaro. What is Manjaro? Yeah, this is awesome window manager. Yeah, I don't know what Manjaro is though. Should I be using it? Is it cool? Let's see. So I think actually, I think this is all good now. Yeah. Looks pretty good. All right, one more. Why not? Because it feels like it's, I don't know, I feel like I'm doing pretty good with decoding here. Okay, so floated arch with an installer. Oh no, this is arch, yeah. Yeah, I haven't really I haven't really configured my arch very much, so it's a little bit, I don't know. It doesn't do everything that I want, but it's like pretty good, and it works really well for coding, I find, personally. So, oops. Let's see, what am I looking at? Yeah. Okay, so I actually made it pretty far. 6442. Let's see if I can find that in here. Oh, there it is. Move L. Yeah. Yeah. All right. So it was 6442. 6442. That's 6443. Move L. 6442. There it is. So pretty straightforward. Yeah, I agree. I used to do well, it's been a long time since I did Gen 2, which is, yeah, kind of insane. The thing I like most about Arch, honestly, is just that the documentation is pretty good. And it's pretty up to date. It's got like all the, yeah, any of the rolling release, that's like the benefit you get. We actually use Debian rolling now at work. Or what is it, Debian? Yeah, I think it's Debian rolling. Let's see, 6442. Yeah, I think that's right. Okay. Oops. And this is a move. Move what? Should be a move at, no at, no plus. And is it a move L? Yeah, move L. There's that 6442, and oh, looks right to me. Yep. Okay. 6045. The upgrade makes a lot of trouble. Yeah, upgrading on Arch is actually pretty straightforward. I haven't been bitten by it. At least I don't think I have. I mean, you have to do it manually, but it seems to work okay. Mostly you just run it from the command line, and it eventually updates all your apps. And but I think you do have to like be careful, because they do. Yeah, if you sort of update blindly, then you might end up with a kind of a screwed up system. So you kind of do want to read the notes. But yeah. $60.45. That's a move W plus. Oh, cool. Okay. So now, yeah, we're totally starting to see the patterns here, which is, this is good. So this is a move W plus. Yeah. That was this one here. Yeah. Okay. And then 6C43. Oh, and that's probably the same one. Yeah, okay, so that's a 3. Yeah, so I'm definitely going to want to factor this stuff out. In fact, I bet that all the 6s look like this. Like, and I can just move all this stuff out. I kind of wish I had a way to confirm that, but for now I'm just going to do it because it's going to make the code a little nicer. Oops. And if it's not true, then I'll move it back. Yeah, that's nice. So I was looking at 643, which if you look at here, 3 is 6-3, so it should be this one, just a straight up move. Is that right? Wait, where is that? After this BRA. Did I make it really far? I'm trying to... Work at Google on Chromium, or are you remote? Or you're just a contributor? I work at Google. Yeah, I've been there for quite a while now. Yeah, it's really cool. It's a great place. You know, and it's fun working on Chrome. Chrome is a really cool project. I mostly work on WebAssembly stuff, not really Chrome. So when I work on this stuff, it's just like fun. Why can I not find what I'm searching for here? I wonder if I can do a... Oh, what happened? I knew I shouldn't have messed with this. Ugh, so annoying. Alright, I needed to sync up somehow. There's an RTS knob. That's probably this here. And there's those minuses. Yeah, so I hit the bottom. That's why I'm not seeing this stuff. It's because I'm past the bottom of this. So let's find what I was looking for. 6C43. Oh yeah, it's way down here. Is making me wonder if I'm missing more stuff that I'm calling word. Probably so. Well, maybe not. EO2. Where's EO2? One CO. Yeah, this is starting to get kind of frustrating. I might try and see if I can find a offline disassembler so that I can continue this without having to futz around with this guy. Yeah, because like where... Oh, there it is, EO2. Okay, STC. Does Google allow employees to set up their OS of choice in their environment, or do they use a uniform config? We have a uniform Linux environment, so we all use Debian testing now. But you can set up your own window manager and stuff like that. So I use Awesome at work. A lot of people just use the default. I guess, I mean, yeah, I'm sure there are people who use Xmonad and all sorts of things. But yeah, I got into Awesome. I like the tiling window manager. I've been thinking that I should switch to, what is it called, i3M? i3W? i3M? But Awesome works for me. and I kind of know how to do it. As far as I know, they basically all use the exact same keyboard shortcut, so it probably wouldn't be too difficult to switch. But I don't know. Why switch? You know. Okay, so I'm looking for OE02, which is STC. OE02, O2. So it's probably this one, OE02. That looks right. Yeah, STC SR. So 0 is kind of a weird one. Looks like sometimes you mask off the low bits and sometimes you don't. So I'm gonna do that. i3WM, that's what it's called. Has a lot less customization compared to Awesome. Huh. Interesting. Yeah, so I don't know. I don't actually use a lot of the customization, so maybe I would be fine just using, using something where most of that stuff is done for me. Yeah, I'm not sure. This is STC SR. And they call it N. Yeah. So where'd it go? There it is. Yeah, so I did it a couple times. It's a bit weird, the output here, though, because it's like, I assume it's saying store the SR into R14, but then it doesn't actually use it. Is that right? Yeah. Or is it the other way around? Is it like STC? Yeah, it writes it into R14. Is R14 like a special register? It might be. No, R14. It's just a regular register. Huh. Yeah, I don't know. BSPWM. Huh. Interesting. This is a dangerous path to take, though, by the way, because, like, exploring new window managers, like, every time I try and do this stuff, it's like a sunk day, you know? So, yeah, there's a part of me that's like, oh, it'd be cool. Maybe it'll be, like, way better tool. But, like, often, it's just like, okay, well, now I'm going to have to learn how to use this new thing. So, I don't know. I might play around with it. I really wish I had a way to know whether or not these were fake or not. Yeah, alright, well. Unix porn subreddit, yeah, I bet. I stick to emudev. I really like that one, although it's pretty quiet. I feel like I should post stuff there more often. Maybe I'll post about this. I don't know. Once it actually can do something, like posting a disassembler is like not super cool. But I don't know, maybe people are into this sort of stuff. I mean, this is how it starts. This is how it all starts. Yeah. Where? Yeah, okay, right. So now I'm at 6BC4. 6BC4. Right, and I'm actually past the end of it here. So that was actually what I was going to do, was I'm going to copy a bunch of this stuff in. So let's just see where that is. 6BC4. Oh yeah, right, it's right there. So we'll just pull that out and copy this part here. And then somehow I lost the stuff here, so I'll just refresh the page. Thank you. Go back to Super H. 2. And copy this in. There we go. Right. Oh, so I actually did this one wrong. This should be R4, not at R4. Yeah, that's this one. 4.3. Yeah. Okay. Next one is move B at R12 plus R11. So it's a move B, and it's a 6-4. Yeah, so this is pretty cool. I like these, like the ones that are laid out in a really obvious way. So I can just do that because I think that'll just work now. Yeah. 6 BBC. Okay, so this is just the C version of that. And that should be, oh, X2. So that's probably sign extension, if I had to guess. Yeah, maybe I should just be using the alphabetical list. That's a little bit easier. X2, 6, C. 6C? Yeah. X2B, RMRN. Oh, X2B. X2B. Yeah. Oops. Let's get rid of that. Oops, wrong one. That one. Okay. 6.4BD. Yeah, so I'm down here now. That's X2W, so it's just 6D. Yeah, so definitely already getting the urge to refactor this stuff, but resisting the urge. 2279. Also, I should check to see if I have any more words. I don't see any, so that looks good. 2279. That's this AND operation. And so it's 2 at the top, 9 at the bottom. Oops. Again, I have a feeling that these all basically follow the same structure because they so far have. So I'm gonna, oops, how did I do that? Vim keyboard shortcuts. Okay, there's our AND. Looks pretty good. Yeah, okay. Looks like the next one is, I really need to convince my monitor not to shut off. Next one looks like add, no, shift. Shift left. I hope this isn't like spazzing out too much for people, because like I like switch between tags like super fast, and maybe it's just like super confusing. I don't know. 321C. So I'm pretty sure this is shift. Let's find that. No. Am I looking at the wrong one? Oh, I'm skipping over that. Yeah, whoops. So 4208. I need to actually implement. So 4208. My guess is oops. Yeah, shift left L2. I wonder what that means. Oh, it's just like shift by 2. Okay. Yeah. Does that look right? Shift L, L2, R2, R1, R1. And there's our, yeah. So this is our X move and shift, move and shift, shift. X move and shift, move and shift, shift. Right, okay. So then 321C is an add, just adding 2 registers. Home stretch. Let's see, there's our 3, and there's our C. 321C, yeah. So we already have one of the 3s here. This is going to be, so you can actually probably just change this to a switch, and I might do that. So that's just adding the 2 registers together. And again, I'm going to make an assumption about the layout of these instructions so that I can do that. Yeah, change them to switches. Maybe I'll do that later. So, but that looks fine. So there's our, wait. There's the add. Yep. 2338. There it is. Test. Cool. But just to make sure, did I miss stuff? Doesn't look like it. Oh, so this is add -1, but I'm calling it add 255, and it's because it needs to be sign extended. Maybe it would be possible to write a script that would use the API of the website to convert the stuff and to compare it versus the output of your script to find the lines which change that word stuff in your script output with the line of online output. Definitely could do that stuff. But you know, it's funny. It's because it's like, if I use the API of the website, that means I have to sort of like decode the API of the website and determine how it works, and then like write a script to do that, and so on. And like this is all going to be more or less fixed at some point. So yeah, there's a part of me that was almost like, it would be kind of a fun thing to do, and I don't know, maybe it's a fun thing to do on stream, but there's a certain part of me that's just like, I'm just gonna slog through it and just get to the stuff that works. Yeah, it really depends on how many instructions there are. Like, I don't really have a sense of how many I've done, you know? What I'm hoping is that, like, a lot of these games probably don't use every instruction. So if I can read through the entire file and parse every single instruction, then, like, how much do I care about decoding the other instructions until I get to them, you know? Like, a lot of my experience working on an emulator, at least on the Game Boy, was that it was much simpler rather than like starting to write stuff and then like you know, not actually having a use case for it. Once you actually have the use case, it's so much easier because you can hit it and you go, oh, okay, now I need to implement this thing. Also, I could support that script, but not this morning. Yeah, I don't blame you. It's probably like, what, 4:30 now? Yeah. Coding at 4:30 for me would be like mostly just staring at the screen with my eyes like, yeah. Big bags under my eyes would not be good. Yeah, so I think at this point we're at test. Yeah, test. Which is this one here. So it's a 2 and an 8, which looks good. So we'll go up to 2. And yeah, again, it's only checking the bottom nibble. So we'll just change that to test. And it's R and an R. I think that's it. Yeah, 427. Yeah, that's not a good time for me. That's the time I should be sleeping. Okay, and then we have a couple more words here. Oh, but those look like they're supposed to be words. So, bing, 2400. That is a real thing. That's a move B. So that's actually 0. Can you give me some examples output of your script with another example output you put into the website? Oh yeah. What's the best way to put that up? Let me finish this instruction and then I'll copy some stuff. 2400. So easy to lose my place. Move B. Move B something at. Yeah, so that's actually pretty nice because it's like BWL. Yeah, so probably it's 345 BWL too. Would make some fun. Yeah, cool. All right, so let's see. Output of the script looks like this. We'll dump it to output.text. That looks fine. And then another example of output you put into the website. Yeah, so that would have been like some of this stuff. Although I've already munged this one a bunch. So let's open the original and copy it out. Make a new file. Start at 480 like we did before. And yeah, I don't know exactly how far I got, but I'm just gonna like, let's say we got down to here. Seems reasonable. Cut that out, and cut that out, and we'll call this data, or binary. I don't know what to call stuff. Oh, this is weird. It's like syntax highlighting my stuff now. Oops. So there's binary. There's output. And yeah, I'll just put them in a gist. Oh, I'm already in new gist. Okay. Binary data. Oops. Casio Loopy disassembler. And we'll just move this over here so no one can see my secret files. Unless it pops up in the other window, but well, we'll see. Oh, it wants me to copy paste anyway. Well, whatever. Okay. So this will be binary.text. This is text, and good. And then there we go. Probably just okay, that looks good. So here's the link to the gist. Copy it in. Feel free to take a look. Okay. So I'm starting to get a little bit tired, so I'm not going to go too much longer, but I feel like I'm doing okay. So I just want to get to the point where I can finish out with the chunk that I'm decoding here. So I have 5F4C. 5F4C. Oh, but I can just look at it here. Oh, did I get much farther? There's a bunch more words here. Let's see. Move L R15. There's a bunch of JSRs. Yeah, there's the JSRs. There's a bunch of, oh, LDS. What is this? That's new. Do I have these add 96? Yeah, I have those. Move L, RTS move L, and then, so how did I miss the LDS? Oh, that's this one. 4F26. So that'll be 2.6. I did this out of order. So this is 2.6. And I'm guessing the F is the 15 and PR is fixed. So we'll just take a look at that. It's LDS. Probably the opposite of SDS. So LDS PR. So there it is, 4 and then 2.6, 26. Yeah. Okay, cool. So LDS L. Add this PR. And I'm kind of like putting commas with spaces in an inconsistent way, but that's fine. So there it is. That looks good. Okay, so then 320 and FF and 0 are all just numbers. 5F4C. That's this one. Ah, yeah, okay. So it's a move L with a displacement. So let's see if we have any other 5s. Ooh, 5 is new. Exciting. So that's a move L with displacement. Should be 0, 1, so it should be this one. Yep. So I wonder if that one is, oh, well, it has to be, right? Yeah, it's another one that's like, it gets the entire prefix. So I'll do it like this. And it's displacement in the bottom. And actually there's another one that worked like this too. Which one was it? This one. And actually it's probably the same where it has this multiplied by 4. Yep. Multiply by 4 plus RM, but that's what this syntax means, so okay. Again, move L displacement to register. So this is the displacement, and this is the register. Yeah. Turn OK. Yeah, should be OK. Oh, right. So this is displacement, and this is what, MN? Where is it? MN, yeah. MN. Yeah, MN. So that's this one, 48R4R15. 48R4R15. Cool. And there's our SDC. There's a 0. That's fine. We have an R4 plus. Okay. And then we have 3000. 3000. Compare equal. Okay. Compare equal. 3000. Okay, so there's this special compare that is immediate, but then there's also this compare register. So that's what we're seeing here. This is compare equal, and it's 3000. So this is just 0. Like that. That is the end of that buffer. Let's look at all the words. Yep, hard to know. Hard to know if there's anyone in there. Like this 45D0 looks like it should be a real instruction, but maybe it's not. I don't know. The rest of them don't really look like real instructions. Like this F, that's not real. These 9s I think are addresses, so those aren't real. E's are probably addresses too. Maybe. Maybe. Not a Git repository. This is great. This is like super new. You can see like, yeah, I can't even. I've got a bunch of empty files here. So I'm gonna basically do all this stuff off stream because nobody wants to see me set up a Git repo. But yeah, I'm pretty excited about this. This is pretty fun. And I'm definitely looking forward to moving forward with this, getting more disassembled. I kind of thought I would get more done in 3 hours, but you know, that's how this stuff works, I guess. Thanks everyone for watching, and I'll try and let everyone know when I'm going to do it again. Thanks.